recording as well. Okay. Hello, everyone. Welcome to my defense talk. The title of my talk is on the role of congestion in distributed complexity. And let's first begin by defining what a typical distributed message passing model looks like. So in distributed message passing models, we are given an n vertex graph G, which specifies the underlying communication network. So the vertices in G are machines, and the edges basically denote point-to-point communication links between the machines. The input is somehow distributed amongst the machines, and this kind of depends on the specific model that we define. And the machines want to compute an output by passing messages to each other in synchronous rounds. So a typical synchronous round looks as follows, and basically the behavior of each machine can be defined by just looking at its local one-hop neighborhood as follows. So you have a machine V and you look at all of its neighbors. So in a synchronous round, it receives messages from its neighbors, performs some sort of local computation, and then it sends messages to all of its neighbors. And this is what happens over all the machines in the graph in parallel in a synchronous round. And we go round by round, basically. So typical model assumptions are that all machines have unique IDs. These are typically assumed to be log n bits. We have perfect synchrony, no faults, that is no machine will ever fail. There's lossless message passing. Whenever you send a message, it will be received at the other endpoint in the next round, basically. And we have infinite local computation power because we are concerned with communication. We are concerned with looking at communication patterns. We don't really want to consider local computation right now. So here are some main obstacles that you will run into when you try to design fast distributed algorithms. The first is locality. So there are some things about the input that you need that are too far away in the communication graph, and you need to wait a certain amount of rounds for that information to reach to you. Then there is congestion, where even if something is close by, there are bandwidth constraints in the network that prevent you from sending or receiving that information through the network, basically bottlenecks. There's asynchrony, where we cannot assume a global clock. You get a lot of timing issues with those. And there's faults where things can break, messages may not be sent to the receiver. Machines can even be actively trying to cause failure by not following your protocol and so on. And in this talk, and even in my dissertation, we only consider models where locality and congestion are the two sort of obstacles that we will face. Asynchrony and faults are considered by many people in the field, in the community, but I do not consider these issues in my dissertation at all. So in the models, these issues are basically defined away by assuming fault tolerance and synchronous message passing. Okay, so let's take two classical models of distributed message passing as an example, which is the local and congest models. So in these two models, the input is basically the communication network, which means a machine is the vertex in the input graph, and what a machine knows is basically like some incident edges or some local information around its neighborhood or something like that. Right? So why would we consider this? So take a working example as the internet. So like a machine or a router in the internet doesn't really know the entire internet graph. but it knows like some local information around it. And it needs to use this local information to basically compute routing trees and shortest paths in the entire internet graph uh, to perform these operations quickly. And that's basically how we're having the Zoom call, I'd say. So in the local model, the main difference is that we have unbounded message size per edge. So in every round, you can send unbounded messages to your neighbors. Whereas in the Congest model, every edge has a log n bit bandwidth constraint. So locality turns out to be the primary obstacle in the local model, and hence that's how it got the name, because there is basically no bandwidth constraint on the network. Whereas in Congest, we get a mixture of locality and congestion because of the bandwidth constraints and the fact that the communication graph can have large diameter. Then we can also look at this massively parallel computation model, or the MPC model. It's a newer model with an all-to-all communication network. So every machine is connected directly to every other machine. So there are no issues with locality because everyone is like one hop away. But these communication links basically have some bandwidth restrictions. So congestion is the main obstacle that we face in this model. So here the input can be anything. It can be graphs, numbers, high dimensional vectors, and so on. And it's basically presented as a theoretical abstraction of modern parallel and distributed systems like MapReduce, Spark, Pregel, and so on. So the title of the talk mentions the role of congestion. And in this dissertation, and even in this talk, we consider models where congestion is the most important obstacle. So the dissertation is basically divided into two parts. The thesis, where part one, we consider the Congest model. And in part two, we consider all-to-all communication models like the MPC model and variants such as the K-machine model and the broadcast congested clique. But for this talk, you only need to keep the Congest model in mind. I won't really talk too much in detail about all the other models. So let's also talk about what distributed complexity means. So there are several measures by which you can measure the complexity of algorithms that you design. These are round complexity, which is the number of synchronous rounds that you take, message complexity, which is the total number of messages you can send, and energy complexity, which could be some function of round complexity, message complexity, and local computation. And the overall goal is to prove upper bounds and lower bounds on a particular complexity measure for various problems in these models. So a short note about upper bounds and lower bounds, how I like to think about it. So lower bounds tell us something about the inherent limitations of these models for solving a particular problem. And they are usually difficult to prove because they argue about all the algorithms that one could possibly design for these models and for solving this problem. But it also gives more insight as to whether we should use these models for solving different problems or whether variants of these models should be used in practice or not. Upper bounds are algorithms, and of course they can be used directly in practice, but there's the asterisk there to say that this may not be as straightforward because these algorithms are kind of designed in these theoretical models, and it might be a challenge to actually port them in practice sometimes. And another theoretical benefit of upper bounds is that they can show that our lower bounds are tight. So we don't need to make more effort to prove better lower bounds. So here is the outline of the talk. We just went over the introduction, and in the next few slides, I'll talk about the chapter 2 in the thesis, which relates to message complexity in Congest model, and I'll talk about some technical stuff we did in this work, and then I'll give a short summary of all the other chapters, and then we'll conclude. So in this chapter, we looked at the maximal independent set problem, or the MIS problem, where we're given an n-vertex graph, G, and we want to find an independent set of vertices that is maximal under inclusion. So before the proposal, we had some results on the message complexity of maximal independent set in the Congest model. And even the proposed problems were related to MIS. But when I started working on these problems after the proposal, they turned out to be a bit too challenging, and there wasn't much we could say beyond what we already knew. So I decided to go in a separate direction and look at a different problem, but very much related to MIS, which is called delta plus 1 vertex coloring. So in this problem, we are given an n-vertex graph with maximum degree delta, and we want to choose a coloring of vertices with at most delta plus 1 colors, such that there is no monochromatic edge. So a proper coloring of the vertices. So here is like a small example where we have a graph with max degree 3, and I've colored it with 4 colors. So this is like a delta plus 1 coloring. So MIS and delta plus 1 coloring are very, very fundamental problems, and they're also related to each other. An important property of problems like these, like MIS and coloring, is that any partial solution that you give me, which is any independent set or any partial coloring, the vertices, you can greedily extend it to a full solution. And this is like a very natural greedy algorithm to solve these problems in the centralized setting. These are called symmetry breaking problems in the distributed algorithms literature, and another name that's used is also locally checkable labeling, because the reason is like any solution that you have can be like locally checked very quickly for correctness. So in this chapter, we are considering message complexity in the Congest model. So just as a reminder, in the Congest model, we have a graph, which is a communication network. We have machines on the vertices, point-to-point communication via the edges, and so on. So the message complexity in the Congest model is just defined as the total number of messages sent by each node in the network throughout the course of the algorithm. We know round and message optimal algorithms for many problems like leader election, minimum spanning tree, minimum cut. And in fact, message complexity for these problems has also been heavily studied in the literature before. But the message complexity of MIS and delta plus 1 coloring has not been studied as much. And all known round efficient algorithms, that is the West round complexity, they require roughly n squared messages, which is the largest, which is pretty high, basically sending a message through every edge in the network. And they typically run in log n rounds. So we want to basically either see why this n squared message bound holds, or maybe design algorithms with lower message complexity. So an important thing that comes up when we try to look at message complexity is initial knowledge. So we can define the initial knowledge of the vertices in two ways. The first is KT0, which is knowledge till 0 hops, where the nodes only know their own unique ID in the network. So recall that every node has a unique ID, login bit ID. And in the KT1 setting, you know your own ID and also the ID of all your one hop neighbors. And because in KT1 you have a little bit more initial knowledge, it's harder to prove lower bounds as compared to KT0. And in fact, we can even notice that message lower bounds in KT0 do not imply anything for KT1 because we basically need theta of m messages to go from KT0 to KT1, which can be n squared in the worst case. Right. So let's see how we could prove such message lower bounds in a very simple setting. Let's consider a deterministic setting where we do not have ID. So basically deterministic congest algorithm, congest model, but with no IDs. So let's take an arbitrary graph G and consider an edge E in the graph. And let's also run a coloring algorithm on this graph. And let's say this edge is colored blue and orange. We take the same graph and same copy of the graph, call it G prime, and run the algorithm over here as well. And we look at the edge E prime, it will have the same color because all the inputs were the same and we were running a deterministic algorithm. So let's say the algorithm did not send a message through this edge E. Let's assume that. And therefore, by the same assumption, it also did not send a message through this edge E prime. Right. So what we can do is we can kind of take out these two edges and rewire them as follows. So the edge E and E prime you can take out and you can rewire them like this. And because there was no message sent through these edges, this new graph, will have the same execution as the previous graph. So basically, the congest algorithm will produce the same coloring on this new graph. And you can already see that there are two monochromatic edges in this graph, which is a contradiction on the correctness of the algorithm, which means that a message must have been sent through the edge E. So we get an omega m message complexity lower bound in the simple setting where we don't have IDs and only consider deterministic algorithms. Things get a bit more complicated when we introduce IDs and randomness and so on into the picture. So let's consider doing the same thing for a KT0 setting. So we have a graph G and a graph G prime. Now we have the two edges, E and E prime, but the endpoints will have IDs, Ij and I prime, J prime. Right, and now if we cross these two edges, we can now, because of the IDs, we can no longer guarantee that these edges will be monochromatic. But at least notice that the initial states of all the nodes, that is when they start, is the same in both the graphs. So what we can do is we can make some additional assumptions on the structure of G that guarantees a particular coloring. And we can do some inductive proof that the states of all the nodes in this graph and in this graph are the same. And then you end up with some monochromatic edge if there is no message sent through E and E prime. Right, and so at least the initial knowledge is the same. So the base case of the induction kind of works out. So we can somehow make things work in the KT0 setting. In the KT1 setting, however, notice that as soon as we cross, the initial knowledge itself changes. So let's consider this vertex I. It had this the ID of vertex J in its initial knowledge. And once we cross, it has the ID of I prime in its initial knowledge. And these two IDs have to be different because IDs are unique in the network. So the initial knowledge itself is different. So no inductive proof would kind of work out in this case. But in any case, we do want to prove a KT1 lower bound. So what we do is we need to work in a restricted model called the comparison-based congest algorithms, where the local computations on these IDs are restricted to be just comparisons. So the way we formally define this, we didn't define this. This was defined in previous work, but the way this is defined is that IDs are stored in special variables, and in these special variables, you can only perform comparison operations. So you can't take like a hash function of the ID or like kind of look at it bit by bit and so on. So this allows us to use a framework that was introduced by Auerbach et al. In the 90s for problems like broadcast, and show a message complexity lower bound for MIS and delta plus one coloring. So it turns out that a lot of congest algorithms are comparison based, where the very famous ones like Luby's and Johnson's algorithms are all comparison based. But some are not, and very prominent examples are the Cole-Wishkin algorithm for coloring rooted trees and the KKT algorithm for a minimum spanning tree. So in this chapter or in this work, we show some new lower bounds. We are able to construct a new lower bound graph and show a unified message complexity lower bound for MIS and delta plus one coloring in the comparison-based KT1 congest model. And this lower bound is n squared. So basically, the KT1 lower bound works as follows. We have the same setting where we have G and G prime with edges E and E prime. And let's say G has nodes with even ID. So the node I has ID 2i and the node J has ID 2j. Now, if this I prime had ID 2j and J prime had ID 2i, then we could cross these edges and the initial knowledge would basically be the same. But because we have to have unique IDs, we basically make them adjacent to the old IDs. So now, before I had a neighbor with ID 2j, now it has a neighbor with ID 2j plus 1. So when I looks at comparisons, these two neighbors will kind of behave the same because their IDs are so close. So how do we get such an ID assignment? So we we construct G as follows. So we have three sets of vertices, X, Y, and Z. There's a complete bipartite graph between X and Y, and a complete bipartite graph between Y and Z. And every set has T vertices in it. And we take the same graph G prime on the right. We assign X to have IDs and even IDs in 0 to 2T, Y to have even IDs in 10T to 12T, and Z to have even IDs in 20T to 22T. And these are sort of arbitrary, but the idea is to keep them super far apart, keep the ID ranges super far apart. And we take X, Y, and Z, so triplets that are X and Z are connected to Y, and we consider this as YZ. And we consider the same triplet in the other graph. And we consider this edge E and E prime, and we want to basically assign the IDs similar to how I showed in the previous slide, where we had simple lower bounds. So when we cross these edges, we want the ID of X prime to be ID of Y plus 1, because Z has its old neighbor was Y, but now its new neighbor is X prime. So for every vertex in X prime, we change the ID as follows. We take the ID of the corresponding vertex in V, subtract the ID of X, add the ID of Y, and add another one. So, and note that X and Y are basically fixed here. So we are adding like a constant to the ID of V in every graph. So the relative ordering of the IDs in X prime is the same as the relative ordering of the IDs in X. The same is done for IDs in Y prime, where we want Y prime to have the ID of Z plus 1. So we change it similarly. So we subtract the ID of Y, add the ID of Z, and add a 1 to everything. And because these IDs are far apart, these ranges sort of don't mix. So the relative orderings of, so X will have the lowest IDs, Y prime, X prime will have the lowest IDs, Y prime will have the middle IDs. And for Z prime, what we do is we just add some huge constant to the IDs, and Z prime will still have the largest IDs in the network in G prime. So what happens now is, because the relative orderings are the same, the colorings in G and G prime will be the same. And then we get this Y prime monochromatic edge. And a similar argument holds for MIS. And using this lower bound graph, we get a n squared lower bound for MIS and delta plus 1 coloring. We also show a new upper bound in this work. We present a n to the 1.5 message complexity algorithm for delta plus 1 coloring in KT1. Of course, this has to be a non-comparison based algorithm because it would contradict the previous lower bound otherwise. And this algorithm runs in square root n plus d rounds. So the message complexity of delta plus 1 coloring in the non-comparison based KT1 congest is n to the 1.5. So the new upper bound is based on a constant round congested clique algorithm by Chang et al. Chang, Fisher, Ghaffari, Witu, and Zheng. So what they do in this algorithm is they partition the vertices randomly into square root delta sets and the leftover set L. And they partition the color palettes also in square root of delta sets. Take a set Vi and let's look at what properties it has. So the induced graph on the vertices of Vi has O of n edges with high probability. And we give the, for all the vertices in Vi, we restricted their palette to be in Ci. And this restricted palette will also have a large enough size, which is delta, the max degree of the induced graph plus 1 with high probability. So we can basically run a log n round coloring algorithm on the nodes of Vi, and it will take O of n log n messages because it has log n edges, and the algorithm runs in log n rounds. Right? And we do this for all the VIs in parallel because their palettes are disjoint. So they don't need to coordinate anything. And this leftover set L, well, what we do is we just recurse on this set of vertices. And what Chang et al. Show is that the number of recursive steps is constant. So the recursion doesn't really add too much to the message complexity. Okay, so what we actually need is the following. A node needs to compute its partition and its color palette without too much communication. And in fact, to run the coloring algorithm in Vi, we also need a node to know its neighbors in the induced graph. So which neighbors are in the induced graph. So a naive way to do this is to just send your partition ID to which partition you belong to send it to all of your neighbors, but that takes too many messages. It takes O of m messages total. We want to do this in a message efficient manner. So what we do is we basically show that all these random partitions can be done by just using log squared and shared random bits. And the nodes can compute these partitions using these log squared and random bits by hashing the values of IDs. So you get a random hash function based on these random bits, and you use your hash the values of IDs to get pseudo random bits, and you basically flip those coins. And this reduction in random bits is is accomplished by showing that the randomized analysis works with limited dependence, basically log n wise independence. And then KT1 information comes to the rescue because we just hash the values of IDs, so we can hash the values of our neighbors' IDs to get the random coin flips that our neighbor makes without any communication. So we know which partition our neighbor belongs to, and we can kind of compute these partitions message efficiently. So the only thing we need to do is we need to figure out is how we can share these random bits throughout the network. And this is done using the construction of a sparse spanning subgraph called a Danner. This is a result by Gimir and Pandurangan in DISC 2018. And this allows us to share, basically broadcast things efficiently throughout the network. So notice that we were hashing the values of IDs. So that's where the non-comparison based stuff comes from. And also using Danner, they do a lot of non-comparison based operations. And in fact, we also kind of discovered a general theme for designing message efficient algorithms in KT1, where we use a small amount of shared random bits and KT1 information to save messages in some operations, and use a Danner to share these bits efficiently. And this general theme we used to get a message efficient algorithm for a related problem called 1 plus epsilon delta coloring. But this doesn't really quite work for MIS, which is a bit of pity.
Shreyas? Give us a little bit of insight regarding the Danner. I mean, how it works and how it's used.
So it basically uses this the same idea as like other spanning tree constructions, where they use these linear sketches. So linear sketches are basically what they do is they were designed in the sketching literature. They are like you take like a matrix and you do some linear algebra, which I can't really describe without a pen and paper. But you basically what you get is for a component. If you have a component, it gives you an outgoing edge. The sketch gives you an outgoing edge in a message efficient manner. So they basically use that, the concept of linear sketches and some other ideas to design these message efficient algorithms.
Okay, thank you.
So Shreyas, maybe you should answer this by saying a little bit about what a Danner structure is also.
Oh, okay. So a Danner is basically a subgraph of the original graph. You can think of it as a spanning tree, but it can be a spanning subgraph. So it has so for a parameter delta, it has n to the 1 plus delta edges. And what you can do is you can compute it in n to the 1 minus delta rounds and n to the 1 plus delta messages. So if delta is 0.5, you can compute it in square root of n rounds and n to the 1.5 messages. And it will have n to the 1.5 edges. So if you do any type of broadcast on this subgraph, it will take n to the 1.5 messages, basically.
Okay, thank you.
I also have a question.
Yeah.
So this it's just a question about your lower bound. Like, so you get the omega n squared lower bound. So does the lower bound tell you that messages have to be sent on most edges, or does it tell you that it's, I mean, does it not tell you that, but just says overall there have to be n squared, omega n
Okay,
squared?
so that's a good question. So for delta plus one coloring, it basically says that the vertices in the middle, they have to send edges on a constant fraction of their edges. And for MIS, actually, it says something pretty interesting, which is if I join the MIS, then I have to talk to a constant fraction of my neighbors. So that's what the lower bound says. Yeah. Any further questions? Okay, so let me just summarize the new results that we discussed so far. So we have a message complexity of MIS and delta plus one coloring using a unified construction in the KT1 comparison based congest model is omega of n squared. And the message complexity of delta plus one coloring in the non-comparison based KT1 congest model is better, much better, which is n to the 1.5. Yeah. And this work is joint work with Gopal Pandurangan, Sriram Pemaraju, and Peter Robinson. So in the remaining time that I have, let me just quickly summarize all the other chapters in the dissertation. So the first part contains two chapters, the chapter 2 and 3. We just saw the message complexity of symmetry breaking chapter in the previous section. And the third chapter considers complexity of optimization problems. And the second part, we have all-to-all communication models where we consider clustering in the K-machine model, connectivity in broadcast congested clique, and ruling sets in the MPC model. So let me say a few words about each of these chapters, and then I'll conclude. So let's look at the third chapter, where we consider optimization on G squared. We show approximation algorithms and hardness of approximations for two problems: minimum vertex cover on G squared and minimum dominating set on G squared. So basically, we have a graph G, and G squared is the power graph where you add an edge between any vertex that has that is two hops away in G. So you add, basically, if a vertex is two vertices are two hops away, you add a virtual edge between them. So so there is this dichotomy of optimization in G squared versus G, where because of limited message sizes, computing on G squared potentially suffers from a lot of congestion than computing on G, because the communication graph is still G, and these extra G squared minus G edges are virtual. You cannot communicate over them, but G squared can have a lot more structure compared to G, which can be exploited to design faster algorithms. So the contribution that we have can be summarized as follows. We analyze the effect of congestion versus structure on these two problems. So minimum vertex cover on G squared becomes easier, and minimum dominating set on G squared becomes a bit harder to solve as compared to the status in G. So in vertex cover, we exploit the structure, and in dominating set, congestion makes things really hard. And this is joint work with Ruven Bar Yehuda, Karen Sensor Hillel, Yannick Moss, and Sriram Pemaraju. The fourth chapter, we consider clustering in the K-machine model. Consider three prominent clustering problems: facility location, P median, and P center. So these two problems, we had to change the name to avoid clashing with the K in K-machine model. We present constant factor approximation algorithms for all these problems running in N over K rounds, which is like the counterpart for efficient in the K-machine model. And we also show matching lower bounds of omega n over k for obtaining even Pauli n approximation. And this is joint work with Sayan Bandyapadhyay, Tanmay Namdar, and Sriram Pemaraju. The fifth chapter is connectivity in broadcast congested clique, where each edge has exactly 1 bit of bandwidth. Here, the best algorithm for connectivity runs in log squared n over log n rounds. And before our work, only log star n lower bounds were known, but we show log n lower bounds for connectivity in this model. And this was joint work with Sriram Pemaraju. And finally, in the sixth chapter, we consider ruling sets in the MPC model. We present sample and gather simulation theorems that allow us to implement congest algorithms in the low memory MPC model. And this simulation theorem allows us to show something like computing 2 ruling sets in log delta raised to 1 over 6 rounds. And this is just one example of the results that we get. And we also consider deterministic algorithms in the linear memory MPC model. And we get 2 ruling sets in log n raised to 4 rounds, so polylog n rounds. And this is joint work with Kishore Kottapalli and Sriram Pemaraj. So, and finally, I'd like to conclude with a few acknowledgements. I've mentioned his name a lot in the last few slides, but I'd still like to specifically thank my advisor, Professor Sriram Pemaraju, for working with me throughout my PhD, working very closely. And there's no words I can say that will like even justify anything. So I'll rather not say anything, but thank you. I'd also like to thank the PhD committee members for your guidance throughout. All co-authors that I mentioned so far, and especially Tanmay Namdar for working a lot with me. We spent a lot of hours thinking about different problems, not just in distributed computing, but in algorithms in general. And I'd also like to thank a few mentors, Professor Kasturi Varadarajan, Karen Sensor Hillel, both of whom are in my committee, and also Professor Rajiv Gandhi for like even motivating me to start a PhD in the first place. I wouldn't be here without your guidance. Finally, I'd like to thank all my friends and family, everyone over here, and everyone who couldn't make it also. Thank you very much. And I'll take any further questions you might have.